Hey, physics students. This is lab 3, I guess. Um, we're just going to analyze the. We don't need any equipment today. We're just going to analyze the data that we took last week on our inclined planes, ramps, whatever you want to call them. So let's go to Blackboard and go to lab. Oh, I don't have lab 3 here yet. Let me go to my computer and open the this is what lab 3 will look like. Uh, so let's see what we have to do. We have to make a graph. This graph is going to be very similar to the graph we made in lab 1, week 1. From the data taken last week, compute the average time for each distance. Construct a table of distance versus time out a calculated column of time squared. This should all sound fairly familiar to you. Find the line of best fit, distance versus time squared. Here we see distance is going to be on the y-axis, time squared is going to be on the x-axis. And paste your graph here, okay? And then with this equation here, we see that if I have y equals mx, t squared is x, 1/2 a is the slope. So I'm going to take the slope that I get from my graph here, and I'm going to set it equal to 1/2 the acceleration and compute the acceleration from that of the ball. Okay, so I need my data from last week so I can show you this. And I have my own set of data. Where is it? Move it over here. Okay, here's the experiment I did. I tilted it at 10 degrees. Actually, I had the same trouble here as I did in the other video. This board is so warped. It was 10 degrees at the top and 9 degrees at the bottom. But anyway, I took a set of data with a tilt of around 10 degrees, and here's what I got. I'd say my angle was more like 9.5 degrees. We'll split the difference. 10 degrees at the top and 9 degrees at the bottom. And here are my 5 times that I got for 10 centimeters, 20 centimeters, and so on. So I need the average of these. So what can I do? I can add a column here. You can do this any way you want. Just with a calculator, just add them and divide by 5. I don't have a calculator. I'm going to insert some columns to the right. Make it a little bit bigger. And I'm going to call this the average time. And I'll put it in seconds. So I think you can do a formula, and probably they have a formula called average. I'll try that. And then I'll put some parentheses. Then I'm going to select these 5 numbers here. Expression is faulty. Maybe it's just AVE. This is all learning experience. Nope. I know what I can do. I can say sum That one's got to be right. Sum divided by 5. 0.43. That looks like the average for this. And then if I copy and paste it here, 0.66, 0.75, 0.86, 0.95, 1.06, 1.13, 1.18. All right, you see my times are considerably shorter than the ones you have. I chose 10 degrees so you guys wouldn't be able to copy my data. Okay, now I'm going to take this distance column and I'm going to make a new table. So I got to go to my new lab write-up, the one for this week. And first I'm going to make a table. All right, insert table. And the number of columns I'm going to have is 2. And the number of rows I'm going to have is, I also need the heading. I'm going to put in 12 rows for right now. And there's my table. And I'm going to call this first column distance. And the second column time. And I'm going to add in a data point that we didn't take last week. But if we just think about it a little bit, we can see that it's a perfectly reasonable data point. I'm going to put the distance in meters. I'm going to switch over to meters for this analysis. And the time I'm going to put in seconds. And if I would have done the measurement at 0 meters, I know what I would have got. I would have got 0 seconds. So I'm going to add that data point in. And then this would be 0.1 meters. And this would be 0.2 meters. And this would be 0.3 meters. And then 0.4 meters. And then 0.5 meters. And then 0.6. 0.7. 0.8. Okay, and what time did I get for, I'm going to cut and paste this from my lab write-up earlier. I'm going to take these times and cut them, or copy them, and paste them into my write-up for this week. Oops. There goes that theory. Pity. I could probably paste the contents, but let's just look at them. 0.43, 0.66, 0.75. 0.43, 0.66, 0.75. You guys are probably much better at this than I am. 0.86, 0.95, 1.06. 0.86, I already forgot. 0.95, 1.06. Notice that these times are shorter than yours, but notice that they're not a factor of 2 shorter. Okay, need 2 more. 1.13, 1.18. 1.13, 1.18. Okay, there's my table. Now I need to make a graph. Well, you have graphical analysis on your device. Let's get rid of these two rows here. I don't. I have it on my tablet. So I'm going to get my tablet and start up graphical analysis. I get it on my lap here. I'm going to choose manual entry. I'm going to do basically the same thing I did in Lab 1. So that was worth it. So can I type here? Maybe I can cut and paste. Let me go to this distance column here and copy it and go to my tablet and paste it. Whoa, cool. So I can cut and paste onto my tablet. And now I'm going to take the times, copy them, go back to my tablet, and paste them. Excellent. Okay, the first thing I want to do is relabel this column options. I want to relabel it distance. And the units are going to be meters. And apply that. Good. Notice that we got kind of a bent over curve here. That's a square root function, by the way. And see, I've got distance on the x-axis. And right now, the y-axis I'm going to call time. And use units of seconds. And apply it. Good. Now, I don't need this, but I'm going to put time on the x-axis and distance on the y-axis. Okay, so this is nice. This is a parabola. This is shaped like a parabola, and that's what it should look like. Great. So I'm kind of confident in my data right now. Now I want to insert a column. I want to insert a column. How do I do that? Oh man, I can't remember. Add calculated column. I'm going to call that calculated column time squared. And the units are going to be seconds raised to the second power. And the expression I'm going to use was ax to the b. I believe that was it. A is 1. B would be 2. So now there's another column here, time squared. Well, this is 0 squared, 0.43 squared, I believe that. So now I'm going to change the x-axis to time squared, and I get a straight line. Fantastic. It's not an exact straight line. It's not bad. If one of your data points is way out of whack here, you might check for errors in data entry, or I don't know, could have a bad data point, could have had some bad stopwatch work. So now I want to get a best fit for this. I believe that was with this little thing down here. Let's look at graph options first. I want to put a title. All my graphs have to have titles. You can title it just after your name if you want. I'm going to call this distance versus time raised to the second power. Good enough. Close that. Here's my title. Here's my axis label with units. Here's my axis label with units. So this graph is looking good. And now I'm going to go to apply curve fit. And it shows a linear curve fit. And I'm going to say apply. So you see this R number, 0.9978. That means that this is a pretty good fit. These points fall very close to the straight line in a relative sense. This is called the root mean square error. We won't use that for anything. Here is the intercept. B is the intercept, negative 0.01594. That's a little off, not much. And the slope is 0.5657. Here's the number I'm interested in, 0.5657. But I need to get this graph into my lab write-up. Well, I could take a screenshot. I could maybe copy it. Uh-oh. Cancel that. That didn't work. Let me see. I'm just going to take a screenshot of it. Here's my screenshot. The screenshot on the in Windows is called Snippet. Snippet might be a good thing for you to look into. You can select an area and take a screenshot of your screen. Take screenshot. All right. And try to get all the units and labels and everything. And I think it put it on my, oh, there's copy to clipboard. Okay, I think it's there. So now I'm going to go back to my lab write-up for this week. Where is it? Right here. Here's my table. And then I'm going to paste in my graph. There's my graph. Now I'm going to take my M value. You've got a different M value. And I'm going to use what equation? It might be behind here. Yeah, here it is. The slope is equal to 1/2 a. So I'm going to take point. This, by the way, would have units of meters per second squared. Right, because the rise over the run, the rise has units of meters and the run has units of seconds squared. So this 0.5657 would be 0.5657 meters per second squared equals 1/2 a. To solve that for a, that's simple enough. I just multiply both sides by 2. So my acceleration would come out to be, I want that to be a small a. My acceleration would come out to be twice that. Hey Google, what's 2 times 0.5657?
The answer is 11,314.
Well, that's not right.
Your phone is not connected to a Wi-Fi network, so I can't help you with that at the moment.
Let me just grab my calculator here. Here's a calculator. Uh, 0.5657 times 2. Easy enough. 1.1314. .1314 meters per second squared. Okay. Now, I know I like to have this stuff in a different color font. I don't like red. How about blue? I guess we could say the same for this table. Okay. This is not taking very long. Now, Galileo, when he did this experiment, he couldn't calculate the acceleration of gravity from this data because he didn't know how to treat a rolling ball. A rolling ball is a special thing because as it speeds up down the ramp, it's also rotating faster and faster and faster. And Galileo didn't know how to deal with that, how to treat that, but I do. And we'll learn about it in later chapters, how you take account of the rotational motion that takes place when an object is rolling along. But I just gave you the formula here for how the acceleration is related to the angle and the acceleration of gravity, which we call little g. So we can actually use our data and angle to come up with a value for g. By the way, the ramps that Galileo had made are still around. They're in a museum in Florence. I've seen them. There's a lot of them, and they're pretty fancy looking. Here's one. So this is in a museum in Florence, Italy. Notice he's got those little bells for when the when the rolling ball would pass those bells or ring a bell. He invented also a water clock. So the way he would measure time was he would take a sack of water with a small pinhole in it, and water would drip out at a steady rate. And so he would let the water drip out while the object was moving, and then he would weigh, using a scale, a balance, he would weigh how much water passed. And that was how he measured time. That's what he used for a stopwatch. He also used metronomes and pendulums to measure time. Anyway, quite fascinating. Also, Galileo's telescopes and everything are in this same museum. Okay, so let's go back to our lab now. What is it? It's this one, I think. Okay, so we're going to use this formula to compute from our acceleration. We're going to compute a value for g. You're going to get different numbers, of course, when you do this because your data is at 5 degrees. You would use 5 degrees in this formula. I'm going to use 9.5 degrees because of my warped board. And this is going to be my acceleration here, which is 1.1314. So I'm going to take 1.1314 meters per second squared. All quantities in lab reports have to have units on them. You'll lose a couple of points. That's equal to 5/7. I'm going to have to do a little algebra here. Times g times the sine of 9.5 degrees. I'm going to use 9.5 for my slope. Kind of the intermediate value between the slope at the top of my board and the bottom of my board. Hopefully you guys were able to find a flatter board. So I'm going to solve this for g. So and see what I get. So that means I'm going to, you can write this algebra out. I'm just going to do it on the calculator. I'm going to take, I'm going to look for clear, there it is. I'm going to do this algebra in my head. 1.1314. I'm going to multiply both sides by 7. I'm going to divide both sides by 5 and see what I get. I get 1.583. Then I'm going to divide this. First, my calculator's in degrees. That's good. So now I'm going to divide this by the sine of 9.5. So here's the sine of 9.5. And I get 9.59. Let's round that to 9.6 meters per second squared. So 9.6 cool. Well, we know from class by now that the acceleration of gravity is about 9.8 meters per second squared. So I got pretty good results, I think. To find out how good our results be, we're going to find the percent difference between our value and the accepted value of 9.8. So that's going to be, if you look in the lab syllabus, there's a formula for percent difference. But it's the absolute value of the difference between the two, 9.6 minus 9.8. 9.6 minus 9.8, which I can do in my head. That's 0.2 divided by 9.8 times 100 to change it to percent times 100%. Okay, well, I can do this. That's 0.2 divided by 9.8 times 100. Grab my calculator, clear it off. 0.2 divided by 9.8 equals that. So that is 0.2. Yeah, it's 2% difference. That's fantastic. So now I'm going to put this stuff that I wrote in blue. Okay, now write a conclusion. These conclusions don't have to be very elaborate. I want them in your own words, though. What you do is you depending on how your results came out, you look at the objective to observe and analyze accelerated and measure the acceleration and compare it to its known value. Well, does this percent difference satisfy you or not? If you came out with a gigantic percent difference and you haven't made any errors, then your data is probably not very good. So comment on what could have gone wrong or what went right. But not more than a sentence or two here. And focus on what the objective was. Each of our labs will have objectives written at the top, and that tells you what you want to focus on in your conclusion. So I'm not going to write the conclusion for you. You can write it. Okay, so then I'm going to save this document so that I can go back to it later. And then I'm going to convert it to PDF, and then I'm going to submit it on Blackboard like we have. And that's it for lab this week. Back to building next week.